Okay, let's get started. Welcome everyone to this deep dive. We're focusing today on really speeding up your grasp of programming fundamentals.
That's the plan.
So, our mission here is twofold. First, we want to get you comfortable with those essential ready-made tools, the built-in functions. Think of them as instant programming superpowers.
Exactly.
And then we'll
Zoom out a bit. We'll look at the bigger picture, the main blueprints programmers use, the major programming paradigms.
Yeah.
These really shape how you structure complex code.
Right. And those built-in functions, it's maybe less about rote memorization and more about saving yourself time strategically.
How so?
Well, a built-in function is just a tool that's already there in the language, ready to go. It does common stuff printing, math, playing with data. So knowing they exist, knowing where to find the right one, means you don't waste time building basic things from scratch. It's the classic, don't reinvent the wheel idea, really.
Makes sense. And our sources seem to group these tools nicely. They point to three main categories we should probably tackle today. Yeah, sounds right.
We've got arithmetic functions, for calculations, games, simulations. Then string handling, which is all about text.
Crucial stuff.
And finally, general utility functions. Things like getting input or working with files, the workhorses.
Good breakdown.
Okay, let's dig into that arithmetic toolkit first. This is where you see the payoff almost immediately, I think.
Definitely. Take the random function. People know it generates numbers, but the real insight is why you'd use it, and crucially, how you pick the right kind of random.
Okay, so it's not just give me a random number.
Not quite. I mean, random is fantastic for unpredictability. You see it everywhere. Games, simulations, even just basic testing.
Right.
But the thing learners sometimes miss is the difference. For everyday tasks, the standard random library is fine. It gives you numbers that look random enough.
Okay.
But if you're doing anything security related, like generating encryption keys, you absolutely need something stronger, something drawing from system-level entropy. That's a key distinction.
That's a really good point. And the examples we saw show how flexible just the basic random tool is.
Yeah, they're useful.
Like getting a neat whole number, an integer between 1 and 10. That's random.random, 1, 10. Simple.
Cool.
But then random.random gives you that floating point number between 0 and 1, much more granular, maybe for detailed simulations.
Exactly. Different needs, different tools within the same family.
And random.choice, my list, just grabbing a random item from a list. Super handy.
Very convenient, yeah. Saves you writing the logic to pick one yourself.
Okay. Next up in arithmetic.
Range.
Range. It's more than just a shortcut for numbers,
How do you mean?
You should think of it as the engine for repetition. It's how you tell a loop precisely how many times to run.
Gotcha. So the example range.
Right. That gives you the sequence 0, 1, 2, 3, 4. It's perfect for loops because programming often starts counting from 0, that 0 indexing thing.
Okay, now this next part seems critical, especially for avoiding subtle errors, maybe in finance or science code. The difference between rounding and truncation. Oh, absolutely. This is a classic aha moment for learners. They seem similar, but the results can be wildly different.
So let's break it down. Rounding first.
Okay, round is about simplification. It adjusts a number to the nearest whole number, or maybe to a certain number of decimal places. Like round 3.141592 gives you 3.14.
It tries to be accurate about nearness.
Exactly. It considers the value of the part you're removing.
But truncation sounds harsher.
It is. Truncation means just chopping off the decimal part. No rounding involved, period.
So 5.99 truncated becomes?
Just 5. The 0.99 is simply discarded.
Wow. And for negative numbers, like negative 3.75.
Truncated, that becomes -3. Again, the decimal part just vanishes.
And that difference, especially with negative numbers, could be huge in accounting or measurements.
Massive. Imagine that difference accumulating over thousands of transactions. And interestingly, you don't always see coders use a specific function like math.trunc.
Oh, what do they do?
A very common trick, almost a shorthand, is typecasting, just forcing the number to become an integer. So writing 3.75 in Python, for example.
And that automatically truncates.
Yep. It throws away the decimal part as part of the conversion. Knowing that little shortcut can definitely speed things up when you're coding.
Okay, that's super useful. Let's shift gears from numbers to text. String handling.
Right. Essential, because so much data, especially anything a user types in, starts out as a string.
First up, concatenation, which just means joining strings, right?
Basically, yeah. Sticking them together.
Yeah.
Everyone learns to use the plus operator pretty quickly. You take a greeting string, add a name string, and you get a message. Simple.
But there's a catch.
There can be, yeah, especially with performance. Using that plus operator over and over again inside a loop, like building up a big string piece by piece, that can be surprisingly inefficient. It creates lots of temporary strings in memory. For high-performance stuff, you'd often use different methods, like specific join functions or maybe buffer techniques.
Ah, okay. So a detail that separates beginner code from more optimized code.
Definitely something to keep in mind as programs get bigger.
Next, length. Seems straightforward, tells you how many characters are in a string.
It is straightforward, but the key thing to remember, as the sources point out, is that everything counts. Spaces, punctuation marks, tabs, they all add to the length.
So if you're checking if something fits in a database field, you can't ignore trailing spaces.
Exactly. That space character is still a character. It counts.
Then there's position, finding where a character is within the string.
Right. And this immediately brings up that concept we mentioned earlier, zero indexing.
Meaning the count starts from 0, not 1.
Precisely. So the first character is at position 0, the second at position 1, and so on. If you're looking for the third character, your code needs to look at index 2.
That sounds like a recipe for off-by-1 errors if you're not careful.
It's a classic source of bugs for newcomers. You really have to hammer that zero indexing concept home.
Okay. And the last piece in the string section is string conversion, moving between data types.
Yeah, this isn't just nice to have. It's often absolutely necessary.
Yeah.
You get input as text, but you need to do math on it, or vice versa.
You need that flexibility.
Totally. The 4 key conversions are really important to know. Turning numbers into strings using string data.
Why would you do that?
So you can print them easily, or maybe combine them with other text labels in a message.
Right.
And then the other way, turning text back into numbers using int text for whole numbers or float text for numbers with decimals.
So you can actually calculate things with user input.
Exactly. Your program would grind to a halt pretty quickly if you couldn't convert that text 10 into the number 10 to use it in an equation.
Got it. Okay, let's quickly cover the last couple of tools, the general utility functions. First, input.
Input. Your direct line to the user. It basically pauses the program, waits for the user to type something at the keyboard, and hit enter.
And whatever they type comes into the program, usually as a string.
Usually as a string, yes. Which is why those conversion functions we just talked about are often used right after input.
Makes sense. And the other one was open for files.
Yeah, open is your gateway to reading from and writing to files. Super common for handling data stored in, say, text files.txt or comma-separated value files.csv.
And it doesn't just read existing files.
No, and this is a really useful feature if you try to open a file for writing, and that file doesn't actually exist yet. Open can often just create it for you.
Oh, that's handy. Good for logging data or saving results.
Absolutely. Foundational for any kind of data persistence.
Okay, so we've looked at all these individual tools, random numbers, string manipulation, file access, really practical, granular stuff.
The building blocks.
Right. But how do developers take, thousands or millions of these little function calls and organize them into something big and manageable, something that doesn't collapse under its own weight?
That's the perfect transition. We've seen the bricks. Now let's talk about the architectural plans. We need to shift from the specific functions to the broader strategies, the programming paradigms.
These are like the philosophies for organizing code.
Kind of, yeah. High-level approaches to structuring your entire program.
Let's start with the one most people probably encounter first. Procedural programming.
Good place to start. Procedural code is structured as a sequence of steps. You have statements grouped into blocks and often organized into procedures or functions, basically, named chunks of code you can call.
And how does it control the flow?
It relies on 3 main control structures. Sequence, you just do this, then do that. Conditional, using S-finality statements to make decisions. And iterative, using loops like for or while to repeat actions.
Sounds straightforward.
It is. It's great for smaller scripts or tasks that are naturally sequential. But its weakness, as programs get really big, managing all the interactions and dependencies can become, well, a bit of a mess. Complexity gets harder to handle.
Which leads us naturally to object-oriented programming, OOP.
Exactly. OOP was developed largely to tackle that complexity problem in large software systems.
How does it structure things differently?
Instead of focusing just on procedures, OOP centers around objects. Think of a class as a blueprint. It defines the properties and behaviors. And an object is an actual instance created from that blueprint.
Like a car class could define color and start an engine, and my specific red car would be an object.
Perfect analogy. And the core idea of OOP is bundling the data, like the car's color, and the behavior that acts on that data, like start engine, together within that object.
Why is that bundling so important?
It helps manage complexity and makes code more robust. If you change something inside the object, it's less likely to break completely unrelated parts of your program. This is helped by key features, like encapsulation.
Encapsulation. Sounds like putting things in a capsule.
Pretty much. It means hiding the internal complex details of an object and only exposing a simple, controlled interface to the outside world. It protects the object's internal state.
Okay, and then there's that big word, polymorphism.
Yeah, it sounds complicated, but the idea is powerful. Polymorphism means many forms.
Okay.
It lets you use the same interface, like a function name or an operator, to work with different types of objects. The system figures out the right specific action to take based on the object it's dealing with.
So less repetitive code?
A lot less. It builds flexibility right in. Add inheritance to that.
Where new classes can inherit features from existing ones.
Right. Reuse code efficiently. Put encapsulation, polymorphism, and inheritance together, and you get a powerful toolkit for building large, maintainable, and reusable software systems.
Okay, that makes sense. What about the third major paradigm? Event-driven programming.
Right. This one operates differently. It's fundamentally reactive. Instead of following a strict sequence, event-driven programs mostly wait for something to happen.
An event? Like what?
Like a user clicking a mouse button, pressing a key, a timer going off, data arriving from a network, things like that.
And how is it structured to handle these events?
It typically has a main loop, often called an event loop, that just sits there listening for events. When an event occurs, the loop triggers a specific piece of code designed to handle that event. These handlers are often called callback functions.
Callback functions.
Yeah, it's just a function you pass to another part of the system, basically saying, when X happens, please call this function back.
I see. So the key features are the events themselves, the event handlers, the event loop.
And this idea of being service-oriented or time-driven, it reacts to external stimuli or internal timers. This is the backbone of almost all modern graphical user interfaces, GUIs.
And web applications too, I imagine.
Absolutely critical for web development. Which actually brings us to some important implications. Developing for the web isn't quite the same as writing a simple program that runs only on your own computer.
What are the extra challenges?
Well, several things. Performance is a constant balancing act.
Yeah.
You want your web app to be fast, but it also needs to work reasonably well on all sorts of devices and browsers. That's platform independence. Then you're dealing with network protocols, specific ways servers and browsers talk to each other, like HTTP. You interact with APIs, application programming interfaces, to use services provided by others. And, of course, security is huge. Your code is out there, exposed.
Right, not just running locally. And there's that distinction between client-side and server-side code.
Yes, a fundamental split. Client-side code, usually JavaScript, runs directly in the user's web browser.
What's that good for?
Things that need immediate feedback, like validating form input before you even send it off, or making parts of the page interactive, little animations, stuff like that.
And server-side?
It runs on the web server, far away from the user. It handles the heavy lifting, interacting with databases, performing complex calculations, enforcing security rules, managing user accounts.
So deciding where each piece of logic runs is a big design decision.
A really big one, yeah. Affects performance, security, everything.
Okay, one last major area to touch on. Code translation. Taking code written in one language and converting it to another, why even do that?
Oh, there are various reasons. Maybe the old language isn't supported anymore, or you need to integrate with a system written in a different language. Sometimes businesses want to move to a language that offers better performance or more features as they scale up.
But it sounds risky.
It definitely can be. It's not just a simple find and replace. We should think about the impact on three groups. First, the users.
How does it affect them?
A sloppy translation might introduce subtle bugs they didn't have before. Or maybe the feel of the application changes in ways they don't expect, even if it technically does the same thing.
Okay. What about the organization paying for the translation?
For them, it's mainly about cost and risk. The translation project itself costs time and money. And there's always the risk that the newly translated code is harder to maintain or have hidden problems that only show up later. It can increase technical debt.
And finally, the developers doing the work.
They face the challenge of learning potentially a whole new language syntax and its quirks. But often the bigger headache is dealing with incompatibilities. A function or library that worked perfectly in the old language might not have a direct equivalent in the new one.
So they have to find workarounds or rewrite logic completely?
Exactly. It can be a frustrating process. It's a significant undertaking, not to be taken lightly.
Wow, okay. We've really covered a lot of ground today, from those tiny, super useful built-in functions all the way up to these big architectural paradigms like OOP and event-driven.
That's right. And hopefully you can see how they connect. Understanding the built-in functions gives you immediate power, lets you code faster today,
Yeah, practical tools.
and understanding the paradigms helps you make smarter decisions about how you structure your code, especially as your projects get more complex. You've got the tools now, and you've got a map of the main building styles.
So where does that leave us? What's the next logical step if you're trying to put all this knowledge together effectively? We've talked about the structure of code, the tools you use within that structure, but what about the stuff that flows through the structure? The data itself.
Ah, good point.
The biggest weakness in any beautifully structured program using all the right tools can still be bad data getting in. So think about this. Before you even get to using a function like int to convert user input into a number, what needs to happen first?
Validation.
Exactly. How do you validate that input? How do you check that it's complete, that it's in the right format, maybe that it falls within an acceptable range? How do you make sure that the data you're about to feed into those built-in functions is actually reliable so the functions don't just crash and burn? That validation step. Maybe that's where the real power to build robust applications begins.